A very good afternoon to all of you. You can unmute your mic and just say what present there.
Good afternoon.
Good afternoon, ma'am.
Good
afternoon, ma'am.
Okay.
Good
Very nice.
ma'am.
Good. So I hope you have understood all the previous lectures. And this module is the last module of your advanced material chemistry course, in which there are 6 portions actually. 6 portions are there in my topic. And this is the chemical measure, trace and ultra trace analysis of any material. Myself Sanjukta A. Kumar, and I am working in analytical chemistry division as the head of chemical method section. And below are the mail ID and my mobile number is written here. Any question, any doubt, you can mail also, as well as at any point of time, you can interrupt me and ask your question. Okay? So to start with, so now this chemical measure, trace and ultra trace analysis has been divided into 6 classes, and in each class I will be covering as per the color code. The first thing I will be covering is, like in this class, the terminology and vocabulary of analytical chemistry, basic overview of analytical concepts, solutions and their concentrations, stoichiometry, sample resolution techniques, gravimetric method of analysis, volumetric, titrimetric analysis, redox titration and potentiometry. So let us go. So now the first lecture content again, because whenever we are starting to read analytical chemistry, there are certain terminologies and vocabulary which we should be well acquainted with, so that we can understand the things without any pause. So therefore, we'll see the various terminologies and vocabulary of analytical chemistry, followed by the what is the concept of analytical chemistry actually, how it goes, and the basic parameters like how to make a solution, how does concentration means, what are the various units of concentrations. And again, since it is analytical chemistry, so dissolution of sample is very important, because ultimately whatever instrumental technique you are going to use, except few techniques which can take directly solid samples, you need to dissolve your sample so that the instrument can take up it, and therefore we need to see the sample dissolution techniques. Then the gravimetric method of analysis, which is the basic analysis which does not require any standard to be used, and it is totally on weight basis. Like we can precipitate some sample, take it weight, and then back calculate the concentration. Then volumetric and titrimetric analysis, and finally the various titrations and potentiometry if possible. So now what is analytical chemistry? You all must be acquainted with the definition. So analytical chemistry is the branch of chemistry focused on the qualitative and quantitative determination of chemical components in a material. So, and you must be knowing what is qualitative and what is quantitative. Qualitative means you just got to know what are the things present in a compound or in a material, and quantitative means how much amount of that component is present. And it bridges the science and application essential in the field like pharmaceuticals, environmental monitoring and material science. So this is the normal definition of analytical chemistry. So what is the role of terminologies in understanding the concepts? As I was telling you, consistent use of terminology ensures clear communication of procedures and results. reduces misinterpretation of data and methods in scientific discussions. And also, it will help in building a strong foundation for advanced analytical methods. Therefore, it is very important to know the various terminologies used in analytical chemistry. So standardized vocabulary ensures consistent across laboratories, whether you are working in India or you may be sometime working in abroad or any laboratory you go. This terminology, whatever you are going to learn today, is universally accepted and as per the IUPAC. So it aligns with international guidelines like ISO or IUPAC for standardized reporting, and it is essential for reproducibility of experiments and validation of methods. So likewise, during your course, whenever you will be reading an analytical chemistry book or any journal, you will discover the use of various terminologies. And so in order to understand these things very clearly, I will ensure that you should be familiarized with all those terms in the due course of our lecture. So first of all, various terminologies are written in the left side, and what does it mean? I have written it in the right side. So analysis. In analytical chemistry course, very often you will find analysis. What analysis you are doing? What analysis you are going to do? Many times this analysis term will repeat. So what does analysis means is the process to provide chemical or physical information about your sample. What you are analyzing? You are analyzing a sample. That means the material being analyzed is called a sample. Analyte. What is analyte then? The component of interest in the sample which is being measured. What is measurand? The quantifiable property of the analyte that is being measured. For example, the concentration of sodium in urine sample is a measurand. Matrix is remainder of the sample excluding the analyte. Contaminants or substance including the analyte itself that is introduced unintentionally into a sample during collection, processing or measurement. So I have given an example here to clarify this better. Say the case of study is determination of arsenic in water. As you may be knowing, arsenic contamination is found in many parts of our India. In groundwater is found to be contaminated with arsenic. That time you need to analyze the water for its arsenic content. So in this case, the analysis is arsenic in water, sample is water, analyte is arsenic, measurand is concentration of arsenic. It is not arsenic, it is concentration of arsenic. Matrix is all other things present in the water except arsenic are called matrix. Say, and what is contaminant in this case? It is not given here. So that if you are looking into this case specially, when you collect the sample for arsenic determination, you must be collecting it in a bottle, bringing it to your laboratory. There you will be keeping it on a table or in a fume hood, and you will be preparing the samples by either acidifying it, and then you are preparing standards to measure it in your instrument. So during this procedure, if somewhere by some means, either through the acid or from yourself or from anywhere in the fume hood, the arsenic compound, some compound is present. So if by any means any external arsenic content will be mixing with this water, then whatever value you are going to get will be erroneous. So in this case, that also is a contaminant, because that I have given in the definition of contaminant: a substance, including the analyte itself, that is introduced unintentionally into a sample during collection, processing, or measurement. So you have to take utmost care so that the sample should not get contaminated. Now, secondly, once you have collected the sample and now you have prepared the sample, there are various other terminologies which comes into picture, like standard. What is a standard? Standard is a substance or material with a known composition, concentration, and purity used as a reference to ensure the accuracy and reliability of analytical measurements. Now, what is primary standard? A substance that is extremely pure, stable, has no water of hydration, and has a stable stoichiometry and known formula weight, for example, NaCl, for chloride determination. So anywhere, if anybody is having any question, you kindly interrupt me and you can ask your question, your doubts, so that finally it will not accumulate. Okay? Then secondary standard, it is prepared by calibrating against a primary standard. For example, standardized NaOH solution is a secondary standard. There is another term which not very oftenly comes, but it comes when you are analyzing using your some ICP OES or ICP-MS or GC-MS, this type of mass spectrometry you are using, or in case of emission spectrometry, there is another term very often used is internal standard. This is added, deliberately added to samples to correct for variations during analysis. How and what we will look in the due course. Now, calibration standards, solutions of known concentration used to create calibration curves. Now, spike is an internal standard or standard addition to a sample or blank. Standard addition is addition of a known amount of analyte, that is a spike, to the sample to provide an internal calibration to the measurement. So now can anybody unmute and tell me what do you understand by internal standard? Or any example can somebody give? Anybody? Who all are present here? Can I take a name? Say Sanchita. Is Sanchita present? Priya? Shubhashish Mishra?
Hello.
Yeah. Can you just tell what do you understand by calibration standard? So whenever we are doing so should I then thought that nobody has understood anything about calibration standard? Okay, then we'll go ahead.
Hello.
Yeah.
I'm RK Shah. The internal, whatever you are calibration standard,
Yeah.
it is used for different concentration for drawing the calibration curve, which will be used next for measurement of unknown solutions.
Good.
So,
Your name is?
Shah.
Shah. Okay, thank you. So now the next is coming. Very often we got confused. You get confused is technique, method, procedure, and protocol. You must be hearing here and there, I am going to use a technique, or I am using this method, or this procedure is given there, this is a protocol, like that. But actually, many persons are in confusion, what does actually these things means. So now let me clearly explain here. Technique is any chemical or physical principle we can use to study and analyze. Next, I will give example, a typical example, and explain all this. Method is application of a technique for a specific analyte in a specific matrix. Then procedure is a set of written directions telling us how to apply a method to a particular sample. And then protocol is set of stringent guidelines specifying a procedure that must be followed if an agency is to accept the result. So now let us look these things with an example. So a method may have several procedures as each analyte adapts it to a specific need, and protocols are common when the results of an analysis supports or defines public policy. For example, when determining the concentration of lead in water under the Safe Drinking Water Act. For example, the lab must use a protocol specified by the Environmental Protection Agency. So this is the clear example which can give more clarity on these terminologies. Technique, say graphite furnace atomic absorption spectroscopy is a technique. And there are various methods which can use this technique, like lead in soil, lead in water, or lead in blood. So all this same analyte is lead, but in one case the matrix is soil, another case it is water, the third case it is blood. For each of these metrics, the methods will be slightly different. So there is 3 different methods even if the analyte is same. Now even lead in water, if we take specifically now in lead in water, it can have different procedures. APHA, that is American Public Health Association, they have procedure for lead in water. Even ASTM, that is American Society for Testing Material. And for India, it is BIS, Bureau of Indian Standards, can also have some procedure for lead in water. So all these are procedures which a standard body is specifying. And when we come to protocol, the same is Environmental Protection Agency. They will give some guidelines. If you are doing lead in water, then you should use these guidelines or you should follow these guidelines. So that time it will be EPA. So next we'll see many other terms like qualitative analysis. The measurements to be determined only the identity, structure, or physical properties of a substance. That time it is qualitative. We just get an idea what are the things or what are the composition of the sample. But quantitative analysis, it is measurements to determine the amount or concentration of an analyte in a sample. So here there is spelling mistake in the measurement, 1M is extra, just you look into it. So it is the quantitative analysis. Now what is signal? It is the measurable response generated by an instrument or detector in proportion to the amount of concentration of an analyte. Say you all must have seen spectrophotometer. Spectrophotometer absorbance is the signal. As you increase the concentration of your analyte, the signal will accordingly increase. So that is the signal. So in case of a spectrophotometer, absorbance is the signal. So now detector. What is a detector? Detector is a device that responds to the presence of analyte, usually generating an electrical output. Like in case of same spectrophotometer, if we will take that example, then there you are getting some absorbance, some value is there. That absorbance is nothing but actually log I0 by IT. I0 is the intensity of light from your source when no analyte is there, and IT is the intensity from the source when your analyte is present. So your analyte is going to absorb some intensity so that the incident light will be decreased to IT. Now whatever your detector is there, any detector is an electrical component. It cannot see the light. Any electrical component can measure either a potential or an electrical current. So this light in the detector, in case of spectrophotometer, what it will do? It will change the light intensity into electrical signal by a photomultiplier tube in case of your spectrophotometer. So now detector is a device that responds to the presence of analyte by changing the signal and usually generating an electrical output so that that can be measured by your instrument. Now total analysis technique. A technique responding to the absolute amount of analyte is called a total analysis technique. Mass and volume are the most common signals, and the corresponding technique are gravimetry and titrimetry. So these are the total analysis technique where normally we do not need a calibration curve or any external standard. Only the mass and volume from where we can calculate our concentration. Concentration analytic technique is a technique in which the signal is proportional to the concentration of the analyte. So all other technique like your spectrophotometer or atomic absorption spectrometer or any mass spectrometer or any electrical like voltammetry, all those things, there your signal is proportional to the concentration of the analyte. So here we have to take some external standard, make a calibration curve, and then found out the concentration of your unknown from this calibration curve. So since most concentration techniques rely on measuring an optical or electrical signal, they are also known as instrumental technique. So all those instrumental techniques are mostly a concentration analysis technique. Now, whenever you are working in a lab and say your superior has given you some analytical assignment, so this is the sample and you need to analyze so and so analyte in this sample. So now, how do you choose an instrument? Whenever in a lab, there may be many instruments present and you need to choose an instrument which is suitable for your analytical problem. So while choosing a method, your consideration is given to some or the other following criteria listed here. So all those criteria I have listed it here. You can see this and then choose accordingly an instrument which will be useful to tackle your analytical problem. First one is scale of operation. What is it? I will explain in my next slide. Then sensitivity, specificity and selectivity, robustness, ruggedness, accuracy, precision, detection limit, linear dynamic range, analysis time. So all these 8 points, like 7 points you take, all these 7 points are actually known as the figures of merit of an instrument. Okay, so these we will see one by one. Now these 3 are ornamental, like analysis time. So definitely you will choose an instrument which will be faster, and again availability of equipment. If you want to do your analysis right now and some person is doing a work in some instrument, so definitely you will not be able to use that instrument. So if another instrument is available and can tackle your problem, then you can go to that. And last but not the least, cost. So we have to see how economic analysis is in a given instrument. So now let us see the various figures of merits one by one. So scale of operation is defined by two things. What are they? One is the amount of sample available. Say whether it is milligram quantity or gram quantity or kg quantity. Some sample is, or in micro level, microgram quantity, some sample is available to you. Say if it is some forensic sample or some blood sample, so that sample amount will be very scarce and you may not be able to repeat your analysis. So that time you have to be very careful. And the second one is the expected concentration of analyte that produces a measurable signal. So what is the concentration of your analyte present in there? Whether it is in ppb range, ppm range, or in percentage level. So these two defines the scale of operation. So collectively, these limitations define the analytical method scale of operation. Like here, you can see this plot where one side it is the analyte concentration and another side it is the weight of your sample. So for example, in a micro trace analysis, sample weighs between in a micro trace means first one is sample quantity. So your sample quantity available is only 0.1 to 10 milligram. And trace analysis means your concentration of the analyte is from 100 ppm to 1 ppb range. So that is the micro trace. This is the micro and here it is trace. So this is micro trace concentration. So like this, your scale of operation is defined. So based on this, you need to choose an instrument which requires minimum amount of sample and is highly sensitive to give a measurable signal in this ppm to ppb range. Okay. Now what is sensitivity? Sensitivity of an then silver for your this experiment. Now what is specificity and selectivity? An analytical method is specific if its signal depends only on the analyte, while selectivity is used when the method is able to respond to several different analytes in the sample. So if to the point we want to say, then the ability to identify an analyte in the presence of other substances in a sample, and also for example an antibody. Specificity is its ability to distinguish. You all know there is an antigen-antibody relationship in biology. So an antibody can attack only a particular, can combine with only a particular type of antigen. So that is highly specific. And selectivity is, say there is a gas sensor and there are multiple gases are there. Among those, it will give a measurable signal with only one gas. So that is selective. It can give signal with all those gases, but there is it must be sensitive to a gas higher than any other gas. So that time it is selectivity is higher. Again, many often we come across the terminologies like robust technique, rugged technique. These two are also quite similar. So for a method to be useful, it must provide reliable results. So however, if you say, then methods are subject to variety of chemical and physical interferences, and that can contribute the uncertainty to your analysis. So a robust method is a method when small and plant changes in condition like slight change in pH, temperature, flow rate, or mobile phase ratio do not affect the result, it is a robust method. And you can use it routinely, because if a method you have made some SOP, standard operating procedure for a method, and you give to your some persons like student 1 and student 2, while doing or while following those SOP, both will follow the same SOP but can get different results. That may be in the uncertainty may not be very high, so that it can be acceptable, and the mean value may approach to your true value. So the method has to be robust for that, because if slight change in pH or temperature or flow rate, it should not get that value should not get affected very much. And what is a rugged method? It is a method when it gives consistent results even when tested by different analysts on different instruments. This is important. On different days, everything is different, or even in different labs. So it shows the method is reproducible in real world conditions. So if you are doing some analysis here and somebody is doing some analysis in, say, in Kerala, somebody is doing in abroad or in US or in some Canada, everywhere, the results should be within the permissible limits. So those type of methods are called as rugged method. So in simple terms, robust is stable despite small tweaks. Rugged is consistent across different people and different setups. Now, accuracy and precision, you must be knowing. Accuracy is defined as the error how closely the results of an experiment agrees with the true or expected results. We can express accuracy by absolute error, that is the average minus true value, and relative error is divided by xt. And then the bias is defined as this is the mean value minus the true value. So it is the population mean for the concentration of analyte, and xt is the true concentration, whatever you got, whatever you have analyzed and got the value, and this is the known value for those sample. Now what is the precision? Precision is the measure of variability between the individual results, because if in one analysis you are doing it multiple times, still you will never get same value. So that difference, the agreement between different values are represented by precision, is called precision, which is represented by standard deviation, variance, relative standard deviation, like this. Now, detection limit is the minimum concentration or mass of an analyte that can be detected at a known confidence level. Mathematically, it is defined as detection limit signal is equal to the blank, average of blank value, plus there is some parameter, this is k into standard deviation of blank. So k is normally taken as 3 as per IUPAC guidelines. So S detection limit is the signal of detection limit, and this is the average signal of blank, and this is the standard deviation of blank. So the corresponding concentration will be signaled by slope of your calibration curve. So this C is the detection limit concentration. Now what is the linear dynamic range? You can see this picture. This is signal versus concentration. This is a typical calibration curve for some instruments, say for your spectrophotometer, you can take. So as you go on increasing the concentration, your signal will increase, but definitely it will, if you go on increasing the concentration to very high, it will, there will be a curvature here. You all must have observed this. Now in this calibration plot, this is the detection limit. This is the limit of quantification from where you have started your calibration plot, and this is the limit of linearity from where the calibration curve starts deviating. Is the limit of linearity. So, and this one is the linear dynamic range from your first concentration you have taken to the point where it is deviating from linearity. So this is the linear dynamic range. And the slope of this calibration curve gives you sensitivity. Now solutions and their concentration, let us see. So concentration is a general measurement unit that reports the amount of solute present in a known amount of solution. The common units for reporting concentration are molarity, formality, normality, molality, weight percent, volume percent, weight to volume percent, parts per million, and parts per billion. So when you are doing trace analysis, ultra trace analysis, that times this ppb or ppm we use very often. Molarity, formality, or normality, these things are used when we are making some acid solutions that time, or if you are doing some electrochemical testing also, sometimes you use molarity, formality. And weight percent, when your analyte concentration is percentage level, that time we very often use this weight percent. Now let me clarify what is molarity and formality. Both molarity and formality expresses concentration as moles of solute per liter of the solution. However, there is slight difference between them. The molarity is the concentration of a particular chemical species, and formality, on the other hand, is a substance total concentration without its specific chemical form. So there is no difference between a compound's molarity and formality if it dissolves without dissociating into ions. For example, take the case of sugar or glucose, where the molarity is equal to its formality. But for a compound that ionizes in solutions such as calcium chloride, molarity and formality are different. When we dissolve 0.1 moles of CaCl2 in 1 liter of water, the solution will contain 0.1 mole of Ca2 plus, 0.2 mole of Cl minus. So the molarity of CaCl2 therefore in the solution is 0, because there is no CaCl2 as such present in your solution. They all have get dissociated into their corresponding ions. However, this solution is 0.1 molar in calcium and 0.2 molar in Cl minus. However, the formality of CaCl2, if in this case I need to tell the formality of CaCl2, then it is 0.1 formal. Since your 1.1 mole Ca2 plus and 0.2 mole Cl minus in mixed, they will give the formality for CaCl2. So this is the difference between formality and molarity. However, this more rigorous definition of molarity is largely ignored nowadays in literature, but you must know when you are working in this analytical field. Now, percent is weight percent, means volume, and volume percent is also there, or weight to volume percent. Weight percent means weight of analyte by weight of sample. Volume percent means volume of analyte by volume of sample, and weight to volume means weight of analyte by volume of sample. So this concentration is units of solute present in 100 units of solution. For example, a solution that is 1.5% weight by volume of NaCl means it contains 1.5 gram of NaCl in 100 ml of solution. Now ppm and ppb. Parts per million and parts per billion are ratios that gives the grams of solute in respectively 1 million or 1 billion grams of solution. So these things are very basic. Actually, I have given here the conversion from ppm to what is it? ppm is nothing but microgram per gram or milligram per liter or microgram per ml. So liter, actually it is milligram per gram, but milligram per kg. But then since for a water solution, aqueous solution, normally we are handling our samples as aqueous solutions, and for water density we normally take is 1. Therefore, the 1 kg is equal to 1 liter. Therefore, we can tell this liter also. So this is the various definitions. So now what is the third thing is stoichiometry. What is stoichiometry? Is the part of chemistry that tells you how much of each substance reacts and how much product is formed. Based on a balanced chemical equation, it is essentially the mathematics of chemical reaction. So now the key idea is a balanced chemical equation gives you moles ratio which act like a recipe. For example, say 2 mole of hydrogen when reacts with 1 mole of oxygen, it gives 2 mole of water. So if you know how much of one substance is present and the stoichiometry of that balanced equation, you can calculate how much of the other substance is required, and by the reaction how much of the desired product is formed. So this is where stoichiometry has important role. So now how you calculate? There are various steps in those stoichiometric calculations. Write and balance the chemical equation. Convert given quantities to moles. Use mole ratios from the balanced equation to relate reactants and products. Convert moles of required substance back to grams, liters, or particles. Let us consider one example. How many grams of water are produced from 4 grams of hydrogen gas? Now the question is, you have been given 4 grams of hydrogen gas, and you need to tell how many grams of water will be formed from this. So what we will tell you need to do, first you have to write and balance the chemical equation. So first you will write H2 plus O2, H2O. So now you have to balance this O, then you have to put 2 here. So now this becomes 4, so you have to put 2 here. So now you have balanced the equation. Now convert your H2 to moles, and you know the molar mass of H2 is 2 gram per mole. So moles will be, because you have given 4 grams of hydrogen, so you have been provided 4 gram divided by 2. So 2 mole of hydrogen are there. So now we have to apply the mole ratios. 2 moles of hydrogen gives 2 moles of water. From this equation you can see 2 moles of hydrogen gives 2 moles of water. Okay. So now convert moles of water to grams. So molar mass of H2O is 18 gram per mole. Therefore, 2 mole of water means 36 gram of water. So now you can tell how many grams of water are produced from 4 grams of hydrogen. You can tell that 36 gram of water will be formed from 4 gram of hydrogen. So this type, by using stoichiometry, you can calculate the required quantity of another reactant and the quantity what the product is going to form. So now you can see stoichiometry is essential in pharmaceutical calculations, chemical manufacturing, environmental chemistry, biochemical reactions, and analytical chemistry also. It ensures that reactions run efficiently without excess waste and allows accurate quantitation. So here I have just given a figure which shows you these are 12th chemistry only, but in one figure it will tell you how much, like various conversions are given here, moles of compound say X, so how much it is in volume and then all. So it is a pictorially I have given all those relations which are actually 12th chemistry but very much required when you are working in analytical field. Now the next step is what are the various dissolution techniques in analytical chemistry. So as during the start of the talk I was telling that when you are using an instrumental technique, maximum instruments takes solution as their input sample. Some techniques are there or some instruments are there which can take solid samples also. But maximum case, you need to first dissolve the sample and make it to aqueous solution so that you can safely use it in a instrument to find out the concentration of any analyte in that sample. So now aqueous dissolution, dissolve the sample in water or buffer solutions. Applications is if your sample is a salt, sugar or any acid, you can only use water to solubilize them. So one example given here is dissolving NaCl in water. If somebody tells you find out the potassium concentration in the salt provided to you, so you are going to use an AS technique. So first we need to dissolve the sodium chloride in water, use a calibration plot for potassium, and then you can find out the potassium concentration is this. This is the most simplest type. Then next is the acid dissolution. Here you use acids like you may be knowing there are various mineral acids which are normally used for dissolution of a sample like hydrochloric acid, nitric acid, HF, HClF4. Those are very used to dissolve the various metal oxides, alloys or minerals or biological materials. So say somebody tells you to find out the impurities in a high purity copper sample. You know copper is used in various industries. So if somebody will provide you a piece of copper metal and tells to find out the impurities present in that, what you will do, you will take nitric acid, dissolve the copper and then bring it in solution form, and then you can use an instrument to find out the various analytes given to you. What is your to find out the various analytes. So this is the applications of metals, inorganic compounds, biological matrices. For example, dissolving steel in aquaresia. Fusion technique. Sometimes the sample needs to be heated with a flux. For example, sodium carbonate, lithium titanate, or lithium metaborate. Lithium, this is lithium morate. So to convert it into a soluble form. Refractory materials like ceramics, if some ceramic material is there, this zirconium boride, titanium boride, or a graphite, all those things need to be fused with some plus. So say dissolving alumina with sodium hydroxide fusion. So you can fuse that, then only they will be dissolving. They will not simply get dissolved with acids. So that time you need to use a flux. you need to first decide whether the sample is acidic or basic, and accordingly you need to use one flux, either acidic flux or basic flux. Alkali fusion use bases, for example, NaOH, KOH, to dissolve organic or inorganic samples like silicates, polymers, so dissolving silica with molten NaOH. So these are the fusion techniques. So there can be aqueous dissolutions, acid dissolution, fusion techniques, alkali dissolution, and more recently, nowadays, people are using microwave assisted dissolution. They use microwave for rapid heating with acids, organic matrix, metals, soils, ores, minerals, so dissolving biological sample for trace analysis. Enzymatic digestion is where you use one enzyme for dissolution of biological samples like proteins, tissues, dissolving proteins with using proteases. You know, proteases are enzymes which degrades these proteins. So they will get solubilized. So that is the thing. And high pressure digestion. So use pressure vessels with acids to dissolve tough samples like rocks, minerals, or glass. Dissolving zirconium silicate with HF in Teflon lined vessels. So these are the various dissolution techniques. Based on the samples given to you, you can decide which dissolution technique will be suitable, and accordingly you can go with the dissolution of the samples. Now, once you have dissolved the samples, you need to prepare standards for calibrating your instrument so that you can find out the concentration of your analyte. So normally we will have a stock solution. Either you make a stock solution from primary standard, or you procure stock solutions from reputed companies like, say, sodium chloride, potassium and sodium chloride, as I was telling few slides ahead before, that if you are giving analytical problem to find out concentration of potassium in sodium chloride, so you need to draw a calibration curve for potassium. For that, you need to have various concentration of potassium, which you need to prepare from a primary standard like potassium chloride, or you can bought a standard from either Merck or any such company which are providing you standards for various elements. So you can take the standards, then prepare calibration, by serial dilution of the standard, you have to prepare a calibration curve. Now calibration standard solutions are often prepared by diluting a more concentrated stock solution. So a known volume of the stock solution is transferred to a volumetric flask. Deionized water was added to make up the volume, and normally the formula used is concentration into volume is equal to N1B1 equal to N2B2. You must be knowing. So here we are not using normality. Normally when you are using a spectrophotometer or AS, we are talking in the term of ppb or ppm. Therefore I have written here is concentration. C0 is the stock solution's concentration, V0 is the volume of the stock solution needed, CD is the concentration of standard solution, and VT is the volume of standard solution. So these are the volumetric flasks where you need to take and make up to the mark, and these are the various vacuum pipettes nowadays normally people use. These type of pipettes are of no use nowadays. Now next is the gravimetric analysis. So after looking into the various terminologies, and we have seen the various terminologies used in analytical chemistry, then we have seen how stoichiometry is used, then the preparation of standards, calibration standards, solutions, their concentrations, and also we have seen how what are the various typical dissolution techniques. With this, now we are going to see the gravimetric method of analysis. This is an absolute technique. It does not require any calibration plot. Quantitative classical analytical method, this is a classical analytical method, not instrumental. Uses only analytical balance and mass is the analytical signal. So based on the formation of a pure, stable and weighable product, the gravimetric analysis is done. Now the principle is that it relies on the conservation of mass. An accurate gravimetric analysis requires that the analytical signal, whether it is a mass or a change in mass, is proportional to the amount of analyte in our sample. It involves precipitation, filtration, drying, and weighing. So the analyte needs to be precipitated by using some reagent. Then you have to separate the precipitate by filtration. Then you need to dry the samples in some oven or in some furnace so that it will form a stoichiometrically stable compound and then weigh it. So now it requires accurate and selective precipitation of the analyte. No other concomitant or matrix elements should get precipitated along with your analyte. Otherwise, it will give an erroneous result. So depending on the various types of precipitates formed, there are various types of gravimetric analysis. Precipitation gravimetry, when the signal is the mass of a precipitate, determination of chloride by precipitating as AgCl. Electrogravimetry, where this is normally coulometry, deposit the analyte as a solid film on an electrode in an electrochemical cell, and the reduction of copper 2 plus to Cu at a platinum cathode. Now you can weigh your electrode before and after the deposition. Volatilization gravimetry, thermal or chemical energy is used to remove a volatile species, moisture content of bread. So that is also a type of gravimetry, how much moisture content is there. So you can now weigh the bread first and then heat it so that moisture will go, and then again weigh it after cooling, and from the difference you can tell, okay, this much moisture was there. Particulate gravimetry, so separating the analyte from the sample matrix using a filtration or an extraction, the determination of total suspended solids in wastewater. So these things are all under the umbrella of gravimetry method of analysis, of which normally the most common is these two, precipitation gravimetry and electrogravimetry. So let us see the precipitation gravimetry. An insoluble compound forms when we add a precipitating reagent or precipitant to a solution that contains our analyte. The precipitate must be of low solubility, of high purity, and of known composition, as its mass has to reflect accurately the analyte's mass. The precipitate must be free from impurities, proper filtration of the precipitates, rinsing the precipitate to remove residual traces of supernatant without incurring loss of analyte due to solubility, drying the precipitates, dry the precipitate to remove residual traces or rinse the solution and to remove any volatile impurity, composition of the precipitate. For a quantitative application, the final precipitate must have a well-defined composition or a stable stoichiometry. So this is the glass tiring rod, like the various setup for your gravimetric analysis. So you can, this is the suction pump, you can filter it properly. Either you can use a suction pump to filter when the precipitates are fine and it is clogging the filter paper. So you can use a suction pump, or normal filtration also we do. Let us see one typical example, determination of magnesium in water and wastewater. So here the magnesium is precipitated as magnesium ammonium phosphate. Using the reagent used to precipitate magnesium is ammonium phosphate. The precipitate's solubility in the presence of dilute ammonia is low. So because of the precipitant is not selective, a preliminary separation of magnesium from potential interferent is necessary. Calcium, which is the most significant interferent, is first removed by precipitating a calcium oxalate. Now the precipitate is isolated by gravity filtration using a rinse solution of dilute ammonia. After filtering, now the precipitate is converted to Mg2P2O7 and wet. So to convert it to Mg2P2O7, you have to heat it in furnace. So this is now a stable stoichiometry. Because previously you can see here 6 water is there. So you do not know, sometimes this can vary. So calculation will not be proper if you are using this to calculate. So this precipitate needs to be ignited in furnace so that finally it will form Mg2P2O7, which has fixed stoichiometry and is stable. So that from here now from the weight you can calculate back the magnesium. However, all analytical techniques are prone to some errors for which we need to take utmost care so that to do it properly. So gravimetry is also prone to error due to co-precipitation, incomplete precipitation, losses during washing, drying, etc. They require a knowledge of conditions for proper precipitation, drying and measurement. So skill is required, high skill is required and practice is required. Applicable to larger sample size, time taken for analysis is long, procedure is rather tedious and applicable only to a limited number of analytes. Next is the volumetric analysis. This is also another type of classical analytical technique. It is a quantitative classical analytical method. Determines the concentration of a substance by measuring the volume of a solution required for analysis for a reaction, also known as titrimetric analysis. Based on a chemical reaction between the analyte and a standard solution known as titrant, the reaction must be stoichiometric, fixed mole ratios, rapid, should occur quickly, detectable endpoint, marked by an indicator or instrumental method. So here the various terminologies used are titrant, analyte, equivalence point and endpoint. I hope you all must be knowing this. Now steps, what are the various steps in volumetric analysis? You need to prepare analyte and standard solution. Add titrant to analyte until the endpoint is reached. Detect endpoint using an indicator or instrument. Use titration data to determine the analyte concentration. Various types of titration are acid-base titration, complexometric titration, redox titration, and precipitation titration. Just see one by one to each. One acid-base titration, I'll directly go to the example. Say now, if say 25 cc of 0.5 moles per liter hydrochloric acid was neutralized by 38 cc of calcium hydroxide. So you need to find out the concentration of the alkali. So now for this, what you need to do? First write a balanced chemical reaction. And this is the balanced chemical reaction where you can see the 1 mole of calcium hydroxide reacts with 2 moles of HCl to form calcium chloride and H2O. So now calculate the number of moles of HCl. So now in the example it has been given that it requires 25 cc of 0.5 moles per liter of HCl. So the number of moles is 0.5 multiplied by this much in liter. So this 0.0125 moles of HCl. Now calculate the number of moles of calcium hydroxide using moles ratio And from the balance equation, you have seen that 1 mole of CaOH whole 2 requires 2 mole of HCl. So now it is 1 mole, 2 mole. So this we have calculated, which is given in the problem, and this we need to know. So accordingly, you can find out that 0.00625 moles of calcium hydroxide is required. So this is where acid-base titration is required to know the acid concentration or base concentration of a given solution. Now, complexation titrations are quantitative analytical methods where a solution containing metal ions reacts with a ligand to form a stable soluble complex with the endpoint detected using an appropriate indicator. Now, based on metal ligand complex formation, the common chelating agent used is EDTA, and is it used to determine the metal ion concentration. For example, determination of calcium 2+ in water. So now what are the various steps? Take a water sample containing calcium ion. You need to use a buffer solution because the pH is very important for complexation of calcium with EDTA. So add an ammonium buffer pH 10 to maintain the required alkaline condition for complex formation. You need an indicator also because neither calcium is colored nor calcium EDTA solution is colored, complex is colored. So add few drops of aerochrome black tea indicator solution which turns wine red in presence of calcium. Now red prior to the endpoint due to the presence of metal indicator complex, and purple at the titration's endpoint, blue after the endpoint due to the presence of on-complex indicator. These three are shown here. This is the A, this is the B, and this is the C. So this is your endpoint. You have to mark it clearly, and that is where an indicator work is there to give the endpoint very clearly. So now here titrate the sample with standard EDTA solution. EDTA chelates calcium ion forming a stable calcium EDTA complex. At the end point, all calcium 2+ are complexed. Indicator changes its color from wine red to blue. Now calculation is done using the EDTA volume to calculate calcium concentration using this formula. Now redox titration, this is another type of titration. A titration method based on oxidation reduction reaction between the analyte and titrant. It involves electron transfer between species, requires a redox indicator or potentiometric detection of at the endpoint. For example, determination of Fe2+ in a solution. You know Fe2+ will get oxidized to Fe3+, and this is the basis of this redox titration. So preparation of reagent. Now standard solution of KMnO4. Prepare a standardized solution of KMnO4 in distilled water. This KMnO4 acts as a strong oxidizing agent in acidic medium which will oxidize the Fe2+ to Fe3+. Now use dilute sulfuric acid to acidify the Fe2+ solution. Now acidic conditions are necessary to ensure the MnO4- reduces to Mn2+ instead of forming MnO2. Otherwise it will form MnO2 and then it will form the precipitate. So you don't need that. So normally you have to ensure that the conditions should be acidic. So what is the oxidation state of manganese here? +7. So +7 to +2. It has to reduce, and in that process it will oxidize Fe2+. If the solution is not properly acidic, then instead it will form manganese in +4 oxidation state, and MnO2 you will get a black color precipitate of MnO2. So now chemical reaction, you can see this is the reaction. In this redox reaction, Fe2+ ferrous ion is oxidized to Fe3 ferric ion. MnO4- permanganate ion is reduced to Mn2+. Indicator is actually, if you know, then KMnO4 itself acts as a self indicator. The solution changes from colorless to light pink at the end point due to the excess of MnO4 minus. So as the procedure, you have to pipette a known volume of Fe2 plus solution into a clean conical flask, add acid, few drop of, because you need to acidify the solution, so you add few drops of sulfuric acid to ensure the reaction occurs in acidic medium. Now you have to fill the burette with KMnO4 solution. Ensure no air bubbles are present in the burette tip. Now you slowly add KMnO4 from the burette to the Fe2 plus solution while swirling the conical flask. Now you know the KMnO4 is purple color. When you add KMnO4 to your conical flask, the Fe2 plus started oxidizing to Fe3 plus and all the KMnO4 will be getting used up. So the color, its purple color will disappearing initially, but at the end point, the light pink color persists. If it is persisting more than 30 seconds, so that is the indicating the end point. So there is a slight excess of MnO4 minus is there, and so that color is persistent. So you need to calculate according to this equation. You have to calculate. So from the balanced equation, the mole ratio of Fe2 plus to MnO4 is 5:1. You can see 5:1. This is 1 mole, this is 5 mole, and this is 1 mole. So concentration of Fe2 plus can be calculated accordingly from this equation. So you just can carefully look into all these things, because this will finally going to like I am going to put some problems based on all these things in your assessment sheets. Now you need to take various precautions when practically doing it, because while writing it is very simple and looks simple, but it does not actually, it requires high skill to do this type of titrations. So you have to be very careful for all these things. Now the next one is the precipitation titration, or titration method where the analyte reacts with the titrant to form an insoluble precipitate. Those type is precipitation titration. This is not very widely used. However, the acid-base titration, complexometric titration, and redox titrations are very common, but the precipitation titration are not so common. Here indicator used, here also some indicator is used. Like, for example, chromate ions are used to detect the endpoint. Example, in Mohs salt method, the chromate forms a red precipitate of silver chromate at the endpoint. Endpoint is determined by the appearance or disappearance of the precipitate or a color change. The reaction requirement, it is must be stoichiometric and rapid. So this is the one example given. Add a known volume of chloride in the solution flask. Add a few drops of potassium chromate indicator. Titrate with silver nitrate until a red precipitate forms of silver chromate. In most methods, silver nitrate reacts with chloride ions to form silver chloride, a white precipitate, and chromate indicator produces a red precipitate of silver chromate after all Cl minus is precipitated. So using this, so that indicates the endpoint. Using this, the volume of AgNO3 calculation is calculate the concentration of chloride minus. So you can see this is the initial phase. Now silver chloride is formed, and when all the chloride ion has been utilized, now your chromate will form silver chromate. So that is the end point. Now it is the potential. We have come almost the last of our talk now. So this is the potentiometry. This technique used to measure the electrical potential voltage of a solution to determine the concentration of an analyte. Principle is the potential difference between a reference electrode and an indicator electrode is measured, which is proportional to the analyte concentration according to the Nernst equation. And applications, you must have worked with the pH electrode, and many ion selective electrodes also are worked on this principle, like sodium, potassium, chloride, fluoride, etc. Now, what are the various components of a potentiometric titration? The reference electrode maintains a constant potential. For example, silver chloride or calomel electrode also is there, reference electrode. Indicator electrode sensitive to the analyte. For example, in this case, glass electrode for pH measurement. pH measurement also is done by some potentiometry. Then salt bridge, which ensures electrical continuity between the two electrodes, and a voltmeter to measure the potential difference. What is the working principle? A titrant is added gradually and the potential is monitored. The equivalence point is determined from the sharp change in potential. The measured potential is related to the activity, effective concentration of the ions in solution via Nernst equation. You all are acquainted, I hope you all must be acquainted with Nernst equation. So, where E is the measured potential, E0 is the standard potential, N is the number of electrons, R is the gas constant, T temperature, and F is the Faraday constant. So these are the references I've used to prepare these slides. If required, both the books are downloadable actually online. This will be available in Google. You can download it and see it. And regarding the potentiometry and electrical and electrochemistry, we'll look more into more details of these Nernst equation on everything will be explained during your 5th class. Okay. Thank you all. And with the talk that the elegance of analytical chemistry lies in its ability to make the invisible visible, I end here the stop. I invite you all for a question session now. You can unmute yourselves if anybody wants to ask some question from anywhere. Anybody is present?
Hello, madam.
Yeah.
Hello.
Yeah.
I'm RK Shah. Madam, please specify the difference between the equivalence point and this uh, completion of
End
reactions
point.
at the end
End
point.
point.
At
End
the
point.
end point.
Actually, equivalence point is exactly where the balance is happening. But it is very difficult to look into it. Let me come. Like in this case.
Okay.
In this case, so it is just slightly extra than equivalence point will be the end point. Then only it will be
Especially it is the potentiometric titration.
Yeah. A potentiometric titration, okay, if you say you are sort of some strong acid-base titration, if you are doing. So near the end point, there will be a sharp change in your pH. Right?
Okay.
So now the middle point of the change. So actually, I'm not having that picture of those points. Can you pinpoint in which case you are asking?
Okay. Just equivalence point. It is. I think it is just near the completion of the titrant and this analyte.
Correct. Equivalence point is exactly where your analyte has completed its reaction with your titrant. But at that point, and your end point is you need to view it like it should be visible to you to know that. Right? Say some color changes with there.
Okay.
Yes,
Okay, madam. Okay. Okay,
anybody
madam.
else? Okay. You are from where? Anybody else? Else you can go through the lecture, and anyway on 7th again we are having a lecture. If you want to ask something, you can mail me so that I can clarify you on all your questions on 7th. Okay, if there is no other question, then we need to end here.